Hi, my name is Michael. I'm a member of the Go team, working primarily on the runtime, and today we're going to be talking about Go garbage collection and how we've made it better with a new technique we're calling green tea. So if you take nothing else from this talk, we made Go garbage collection faster, and we plan to make it generally available in Go 126. You could leave, walk out of the room now, but I'm not going to tell you why it's called green tea until the end, so stay in your seats. So before we can talk about green tea, let's all get on the same page. So the purpose of garbage collection is to automatically reclaim and reuse memory no longer used by the program. And to this end, the Go garbage collector concerns itself with objects and pointers. Objects are Go values whose underlying memory is allocated from the heap. And objects are created when the compiler can't figure out how else to allocate memory for a value. To figure out whether objects are still being used, the garbage collector looks at the pointers that refer to these objects. Pointers are, of course, the memory addresses of Go values. So Go's garbage collector follows a strategy broadly referred to as like tracing garbage collection, which just means that the garbage collector follows or traces the pointers in the program to identify which objects the program is still using. And more specifically, the Go garbage collector implements the mark sweep algorithm, and this is much simpler than it sounds. Imagine objects and pointers as a sort of graph in the computer science sense. Objects are nodes, pointers are edges. The mark sweep algorithm proceeds, as you might expect, in two phases. Marking is the first one. So marking consists of walking the object graph from well-defined source edges called roots. So think like global variables, local variables, that sort of thing. And then we mark everything we find along the way as visited in order to avoid going in circles. And so this is your typical graph flood algorithm that you might remember from like a computer science course, a depth first search or a breadth first search, something along those lines. So once we're done with that, we reach the second phase, the sweep phase. And whatever nodes were not visited in our graph walk are considered unused or unreachable by the program. And we call this state unreachable because it's impossible with normal, safe Go code to access that memory, simply through the semantics of the language. So we iterate through all the unvisited nodes and mark that memory as free to the memory allocator. So you may think I'm oversimplifying here a bit. It's just a graph flood, but garbage collectors are frequently referred to as magic and black boxes. And like, don't get me wrong, there are complexities. Like, for example, this algorithm, we run it concurrently with your program. So walking a graph that's mutating underneath you brings challenges. We're also able to parallelize this algorithm that brings its own complexities, and that's a detail that'll come up again later, but only briefly. But trust me that in general, like when I tell you these details are mostly separate from the core algorithm, I mean it. Like it really is just a simple graph flood at its center. Very easy to implement and understand. So let's go over a simple example. Here we have a diagram of some global variables and a Go heap. There's a lot going on here, so bear with me for a moment. But this is important since we're going to be using this example throughout the talk. So let's break it down piece by piece. On the left, we have our roots. These are global variables x and y. They're going to be the starting point of our graph walk. And since they're marked blue, according to our handy legend in the bottom left, they're currently on our work list. On the right side, we have our heap. Currently, everything in our heap is grayed out because we haven't visited any of it yet. Again, according to the legend in the bottom left. Each of these rectangles represents an object. Each object is labeled with its type. This object in particular is an object of type T, whose type definition is in the top left. It's got a pointer to an array of children and also some values. So we can surmise this is some kind of recursive tree data structure. In addition to the objects of type T, you'll notice that we have array objects containing star T's. These are pointed to by the children field of objects of type T. Each square inside of an object represents 8 bytes of memory. A square with a dot is a pointer. If it has an arrow, then it's a non-nil pointer pointing to some object. And if it doesn't have a corresponding arrow, that's of course a nil pointer. Next, these dotted rectangles represent free space, what I'll call a free slot. We could put an object there, but there currently isn't one. You'll also notice that objects are grouped together by these labeled, dotted, rounded rectangles. Each of these represents a page, a contiguous block of memory. In this diagram, we see that each object is allocated as part of some page. Like in the real implementation, each page here only contains objects of a certain size. This is just how the Go heap is organized. Finally, these pages are labeled A, B, C, and D just for convenience, and I'll refer to them that way. Pages are also how we organize per object metadata. Here you can see 7 boxes, each corresponding to the 7 object slots in page A. Each box represents one bit of information, whether or not we've seen the object before. This is actually how the real runtime manages whether an object has been visited, and it'll be an important detail later. All right, thanks for staying with me. That was a lot of detail after I just told you not to sweat the details, but I promise this will all come into play later. For now, let's just see how our graph flood applies to this picture. Start off by taking a root off of the work list. We mark it red to indicate that it's now active. Following that root's pointer, we find an object of type T, which we add to our work list. Following our legend, we draw the object in blue to indicate that it's on the work list. And note that we also set the scene bit for that object in our metadata. Same goes for the next root. And now that we've taken care of all the roots, we're left with 2 objects on our work list, so let's take one off the work list. And what we're going to do now is walk the pointers of this object to find more objects. And by the way, we call walking the pointers of an object scanning that object. So we find this valid array object, add it to our work list, and from here we proceed recursively. We walk the array's pointers, find some more objects, and then we walk the objects that the array object referred to. And note that we still have to walk over all the pointers, even if they're nil, because we don't know whether they're going to be nil ahead of time. So one more object down this branch. And now we've reached this other branch of the heap. And starting from that object in page A, we found much earlier from one of the roots. So you might be noticing a last in, first out discipline to our work list here, indicating that our work list is in fact a stack. And since our graph flood is approximately, and that suggests our graph is approximately depth first. This is intentional and reflects how the actual graph flood algorithm works in the Go runtime. So let's keep going. We'll find another array object, we'll walk it, and just one more object left on our work list. We scan it, and finally, we're done with the mark phase. There's nothing we're actively working on, and there's nothing left on our work list. Every object drawn in black is reachable, and every object drawn in gray is unreachable. So let's sweep the unreachable objects all in one go, and we've converted those objects into free slots ready to hold new objects. So after all that, I think we have a handle on what Go garbage collection is actually doing. So let's get on with the core of this talk. If you've tuned out the first part because you already know about garbage collection, this is me telling you to pay attention again. All right, so why does any of this need changing? Well, it turns out that we can spend a lot of time executing this particular algorithm. I'm sure many of you have come across GC CPU issues in your time working with Go. And the thing to understand about the cost of the garbage collector, there are 2 parts to it. The first part is how often it runs. And the second part is how much work it does every single time it runs. Multiply these 2 together and you get the total cost of the garbage collector. So for the first part, how often it runs, not going to go into that. I did a GopherCon EU talk in 2022 about Go memory limits, touched upon that a little bit. Look at that, other resources to learn more about that. For this talk, we're going to be focusing on the second part, what the garbage collector is doing every single time that it runs. And what it's doing is it's spending most of its time on marking and scanning objects in the mark phase. That's why I didn't even bother explaining the sweep phase much. In practice, sweeping is very, very cheap since we designed it to be that way. It's also much easier to design it to be that way. And at the heart of why marking is so expensive is that it's a poor fit for modern CPU microarchitecture. At least 35% of the time marking is spent just waiting on the CPU to fetch memory. On its own, that's already pretty bad, but it totally gums up the works and makes modern CPUs fast. So what do I mean by gum up the works? Well, the specifics of modern CPUs can get pretty complicated, so let's use an analogy instead. Imagine the CPU driving down a road where that road is your program. The CPU wants to ramp up to a high speed, and to do that, it needs to be able to see far ahead of it, and the way needs to be clear. But the graph flood algorithm is like driving through city streets for the CPU. The CPU can't see around corners, and it can't predict what's going to happen next. To make progress, it constantly has to slow down to make turns, stop at traffic lights, avoid pedestrians. It hardly matters how fast your CPU is, how fast your engine is, because it never really gets a chance to get going. And let's make that more concrete by looking at our favorite diagram. I've overlaid the heap here with the path that we took. Each left to right arrow represents a piece of scanning work that we did. And what I want you to notice is that we were jumping all over memory, doing tiny bits of work in each place. In particular, we're frequently jumping between pages and between different parts of pages. Modern CPUs do a lot of caching. Going to main memory can be up to 100 times slower than accessing memory that's in our cache. CPU caches are populated with memory that's been recently accessed and memory that's nearby to recently accessed memory. And so we want to take advantage of that. But there's no guarantee that any two objects that point to each other will also be close to each other in memory. The graph flood certainly doesn't take this into account. Quick side note, if we were just doing slow memory accesses, it might not be so bad. CPUs can issue memory requests asynchronously, so even slow ones could overlap if the CPU can sort of see far enough ahead. But in the graph flood, every bit of work is small and highly dependent on the last, so the CPU is forced to wait on nearly every individual memory fetch. And unfortunately for us, this is only getting worse. There's an adage in our industry of wait 2 years and your code will get faster. But Go, as a garbage collected language, relying on the mark sweep algorithm risks the opposite. Wait 2 years and your code will get slower. New hardware is adding challenges to garbage collection performance in general. And for one, memory is more complicated. Memory tends to be associated with subsets of CPU cores. Accesses by CPU cores outside of that subset to the same memory are now slower than they were before. In other words, the cost of a main memory access now depends on which CPU core is the one doing the accessing, and we call that non-uniform or non-uniform memory access, or NUMA, if you've heard the term before. The graph flood doesn't take this into account at all. Memory bandwidth is becoming more constrained, and all I mean by memory bandwidth is how many memory requests can an individual CPU issue, right? And so we have more CPUs, but each can submit relatively fewer requests to main memory, and so you have more requests waiting if you're talking to main memory all the time, like the graph flood is. Also, remember I told you the graph flood is happening in parallel, right? And we have this work list data structure, and it is sharded to some degree, but it's also a shared work list, right? There is a shared component of that, and that needs to be able to scale more gracefully to more CPU cores. Just throwing a lock on it is definitely not good enough. Finally, new hardware has fancy features like vector instructions, which let us operate on a lot of data at once. And this has the potential for big speedups, but we have absolutely no idea how to apply that to market. So we're leaving something on the table by not accessing all this new hardware that's appearing. Finally, this brings us to green T, our new approach to the mark sweep algorithm. The key idea behind green T is astonishingly simple. Work with pages, not objects. Sounds trivial, right? And yet it took us years to figure out how to order the object graph walk and what we needed to track to make this work well in practice. And what this actually means is, 1, instead of scanning objects, we scan whole pages. 2, instead of tracking objects on our work list, we track pages. And 3, we still need to mark objects at the end of the day, but we'll track that locally on each page rather than across the whole heap. So let me show you what I mean. Back to our favorite diagram, we've got just one difference from before. We now have 2 bits of metadata per object per page. Again, each bit or box corresponds to one of the object slots in the page. In total, we now have 14 bits that correspond to the 7 slots in page A. The top bits represent the exact same thing as before, whether we've seen the object or not, and I'll refer to these as the seen bits. The bottom set of bits are new. They're going to tell us whether we've already scanned the object or not. So this new piece of metadata is, of course, going to come in handy because we're going to run our algorithm this time by tracking pages on the work list and not objects. That extra bit of metadata per object per page will help us identify what we actually need to look at in the page when we go to scan it. Right. Without further ado, let's begin the mark phase. Start off the same as before, walking objects from the roots. But this time, we're going to put a whole page on our work list. In this case, page A, and that's why it's shaded in, the whole page is shaded in blue. The object we found is also shaded in blue to indicate that when we do take this page off the work list, we will need to look at that object. Note that the object's blue hue directly reflects the metadata in page A. Its corresponding seen bit is set, but its scanned bit is not. All right, let's continue. We follow the next route, find another object. Once again, we put the whole page on the work list. Now page C is shaded blue. Next, we take page A off the work list, and we see that there's only one object to visit for page A, so we look at its pointers. And as a result, we add page B to the work list since the first object in page A points to an object in page B. Next, we take page C off the work list. Let's process the object in say page C now, and we found another object in page B, which is already on the work list, so we don't need to add it to the work list. But we still need to mark the object we saw as seen to indicate that we'll have to look at it later when we process page B. And well, it's page B's turn now. So we've accumulated 2 objects to scan, and we process both of these objects in a row in memory order. So we walk the pointers of the first object, and we're going to find a bunch of objects in page A. So we put page A on the work list. We handle the second seen object in the page immediately after, find a few more objects in page A, and now it's time to process page A. Notice how now we only need to process 3 objects, not 4. Page A is back on the work list and back on sort of in our active thing, but we're making progress. We don't need to redo the ones that we did before. And again, how do we know that? It's the difference between the seen and the scanned bits that tells us what we need to do. All right, let's just quickly process the rest of these, and we're done. There are no more pages on the work list, and there's nothing we are actively looking at. Notice that the metadata now all lines up nicely since all these objects were both seen and scanned. You may have noticed during our traversal that the work list order is a little bit different from before. Where the graph flood had a last in, first out, stack-like order, we're now using a first in, first out, queue-like order for the pages on our work list. This is intentional. We let seen objects accumulate on each page while the page sits in the queue, so we can process as many as we can at once. That's how we were able to hit 3 objects in a single page scan on page A toward the end. Sometimes laziness is a virtue. Finally, we can sweep away the unvisited objects as before. So, let's come back to our driving analogy. Are we finally getting on the highway? Let's recall our graph flood picture from before. We were jumping around a lot, doing lots of little bits of work in different places. And with green tea, it actually looks a lot better. What I want you to focus on in this picture, in particular, is the long, clean left to right arrows across pages A and B. The longer these arrows, the better. And with bigger heaps, this effect can be even stronger. And that's the magic of the algorithm. That's our opportunity to ride the highway. More concretely, this all adds up to a better fit with the microarchitecture. Clearly, we have a much higher chance of objects that are located next to each other in memory actually being looked at the same time. Simultaneously, we're accessing the metadata for the page at the sort of, we're much more likely to access to access metadata that's already in our cache because we're processing a bunch of objects in the same page at once, and all that metadata is kept together. Also, tracking pages means our work lists are smaller in general. I mean, we have to add things back to the work list, but the length of the work list is smaller, so we put less pressure on it, especially when we're like sharding it across different threads, and that means less contention and fewer stalls, better scalability. And speaking of the highway, now we can take our metaphorical engine into gears we've never been able to before, since now we can use vector hardware. So if you're only passively familiar with vector hardware, you might be confused as to how we can do any of this stuff with it. Usually you hear about vector hardware in the context of like fancy math and AI or media applications. And I'm saying vector hardware to be very general, but I mean like SIMD. Like SIMD is what you usually hear. But the truth is we don't care about the fancy math. Like what we do care about is the fact that we get access to larger registers, like 512 bits wide instead of our usual 64 bits. And this is actually enough for us to hold all of the metadata for an entire page in just 2 registers right on the CPU. This wasn't even an option for the graph flood, where we'd be jumping between scanning objects that are all sorts of different sizes. Sometimes you'd need 2 bits of metadata, and sometimes you need 10,000. You wouldn't know until you actually got there. That's still not quite enough, though, to make this work. To make like marking work well with vector hardware. To actually make this work in practice, we need access to some powerful bit manipulation instructions that are only available on more recent hardware. I won't go into the details since it's somewhat complicated and outside the scope of this talk, but come talk to me after if you're curious what Galois fields have to do with garbage collection. All you need to know for now is that 1, we figured out how to do it, 2, it works well, and 3, you can only do this on newer hardware like AMD Zen 4 or Intel Ice Lake in terms of x86 hardware, if the CPU generations mean anything to you. All right, so that's it for how it works. How much does this actually help? It can be quite a lot, actually. We're seeing reductions in garbage collection CPU costs between 10% and 40% in our benchmark suite. 10% reduction is what I would say is the modal improvement, speaking anecdotally, just people that have reported back to me, and I've sort of looked around. But it's really hard to give a concrete average because it turns out it's very workload dependent. However, we just rolled this out into most of Google, and we're seeing really promising results. Also, vector hardware gets us another 10% roughly, at least when it applies. That's awesome. It's not all perfect, though. Like I said, it's workload dependent. So more specifically, we know that some workloads don't benefit from this strategy. At the root of the work is really the hypothesis that we can accumulate multiple objects on a single page before we scan the page. This is clearly the case if the heap has like a very regular structure, objects of the same size at a similar depth in the graph. But there are workloads that require us to essentially scan only a single object per page at a time. This is potentially worse than the graph flood because we might be doing more work than before, simply trying to accumulate objects on pages and failing. But we worked around some of the early issues here by, for example, adding a fast path for pages which only have a single object to scan, which helped to reduce and eliminate some of the regressions early on. On the brighter side of things, though, we learned that page scanning is a lot more applicable than we initially expected. That even at relatively low densities, like even if we're only scanning 2% of a page at a time, that can yield significant improvements, which is pretty motivating. All right, I hope by this point you're all excited and buzzing in your seats, eager to get your hands on green tea. So I'm happy to announce that in Go 125, green tea is already available as an experiment. You can set the environment variable go experiment to green tea GC at build time to enable it. We expect to make it the default in Go 126, and this release will also come with the vector acceleration I mentioned before. I'm not done yet. I'm not done yet. Hey. I've spent all this time talking about the hard technical details, right? But I want to talk a little bit about the journey and the human element of this technology. And yeah, I promised I would tell you why it's called green tea, and you all already started clapping. You didn't even know. So I guess you are really all in your seats, buzzing and excited to get your hands on it. All right, so when I introduced green tea earlier, it was this single, simple idea, like the spark of inspiration that just one person had. That's not true at all. So much of this work we've done has had input from so many different people over the years, and it's been like 7 years. There were a lot of ideas that didn't work, and there were a lot of details that needed figuring out just to make this single, simple idea viable. The seeds of this idea go back all the way to 2018, and what's funny is that everyone on the team that I talked to thinks someone else thought of the idea, which is probably a good sign, actually. I promised I'd tell you how green tea got its name, and it got its name in 2024 when Austin, our wonderful Go tech lead, worked out a prototype of an earlier version of green tea while cafe crawling in Japan and drinking lots of matcha. That's it. This prototype showed that the core idea of green tea was like viable, and from there we were off to the races. So throughout 2025, I implemented and productionized green tea. The ideas evolved and changed even further, and this took so much collaborative exploration because the thing about green tea is it's not an algorithm. It's an entire design space, one that I don't think any of us could have navigated on our own. It's not enough to just have the idea, but you need to figure out the details and prove it. And now that we've done it, we can finally iterate. After years of banging our heads against our desk, we can actually iterate on the problem of garbage collection performance, which is really exciting. So the future of green tea is bright. All right, so please try it out by setting go experiment equals green tea GC and let us know how it goes. We're really excited about this work and we want to hear from you. Thank you.